want to. I'm also going to record it because Alyssa's not here. So, all right, so what we're going to do is put together all these building blocks we have to see if we can figure out how to find the range of a projectile. Okay? So, the two example problems I have, the first one is a mortar is fired at 70 meters per second at an angle of 30 degrees. Okay, so somebody fires a mortar, and I want to know how far does it go horizontally? And because for mortars and tank shells and rocks and cannonballs, air resistance is not a big factor, these calculations actually turn out to be fairly accurate. So it's not just sort of, a pretend exercise. You can actually use these. So the first thing I'm going to do is draw a diagram. And you guys have got to do it first. If your diagram is off to the right in the margin, I'm not going to count it. It's got to be the first thing you do. Think about the path the projectile takes. So if you have a mortar and it's on level ground and it's fired, it is going to travel in a path that looks something like this. It's going to start here, it's going to go up, 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 down, down, down. It's going to follow a parabola. Because the ground is level, it's going to land at the same height it started at. Okay? So I want to see the path of the projectile. I want you to think about it first. Now, you need to add a coordinate system. You need a reference. So it makes most sense to call this direction y and this direction x. So impose a coordinate system on your diagram. Okay? So that's where you start. That's not what you tack on at the end in the corner on the side smaller than a thumbtack. All right? Now, from the problem, we can tell two things. We can tell that the initial velocity of the projectile is 70.0 meters per second, and the angle at which it's launched at is 30 degrees. Okay? So, I've already stamped my variable list on there to save time. What do we know in this variable list? There's a couple things we know. Any volunteers? Yes, Ben.
The initial velocity of y is 0.
It's not. At the beginning of the problem, is this thing moving sideways, horizontally? It's not. It's moving at an angle, right? If I launched it horizontally at the beginning of the problem, it wouldn't be moving up or down. But at the beginning of this problem, it's moving up and over, right? Moving this way and that way at the same time. If there was no gravity, in the first second, it would go 70 meters. It would go 35 meters that way and 60 meters that way. Okay? So it's not 0, so we don't know that one. Done. But there's some easy ones we do know, guys. What are they? Yes, Zach. The acceleration in the y direction is always negative g. Okay? That's always going to be true. And that makes it obvious the other one we know, which is? Tim? Get the earbuds out. What else do we know, Tim?
I wasn't paying attention.
Come on, help me here, guys. Yes, Jackson.
The acceleration of x is 0.
The acceleration of the x is 0. There you go. So those we know. There's one or two others. One other thing we know. What is delta y? How high is it at the end of the problem relative to where it started? Sophie? It's 0. Delta y is 0 meters. It ends at the same height it starts at, in the y direction. Delta x is not 0. It ends over here. It started over here. That's not 0. But delta y is 0 in this case. You see that? So delta y is y final minus y initial, which is 0 minus 0. Okay? All right. I think that's all we know. So now we're going to start our multi-step solution. Okay? So step 1, we have got to find the velocity in the y direction initial, because it's not going to be 0. Okay? So in order to find the velocity in the y direction, we can use the fact that the velocity in the y direction equals the initial velocity times the sine of theta. That's what we worked on yesterday, right? And I wish there was more time to do a whole lesson on trig and connect all those dots, but we're just going to use it because we're trying to fly through this. But how fast it's moving upwards. So we've launched this sucker like this. It's moving over and it's moving upwards initially. If you know the angle and you know the hypotenuse, which is the initial velocity, then the initial horizontal velocity you can use by using cosine, because cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse, so you can find the sine. So I think you guys wrote those in your toolboxes, is that right? I think you put that in your toolbox right there. Okay? So we can just evaluate it. That is going to be 70.0 meters per second times the sine of 30 degrees, which is 35.0 meters per second. That was the warm-up problem, right? So that's how fast it's going upwards at the beginning of the problem. We can also figure out how fast it's going horizontally. So we can find the velocity in the x direction initial. That's the initial velocity times the cosine of theta. You guys have those in your toolbox, right? If not, put them in there. That and that. This is going to be 70.0 meters per second times the cosine of 30, which was, remember, go ahead and do it again and keep it on your screen because we're going to need it. I think it's 60.6 maybe? 60.6 meters per second. Is that close? Okay. How long is it going to be in the air? Any guesses? Can you make an informed guess? If I throw a rock upwards at 20 meters per second, how long is it going to be in the air? Roughly? Well, what does gravity do? Gravity decreases the velocity by about 10 meters per second every second, right? So if I throw a rock upwards at 20 meters per second, after 1 second, what will be its velocity? 10, right? After 2 seconds? 0. After 3 seconds, negative 10. And after 4 seconds, negative 20, right? So it takes 2 seconds to stop moving up, then another 2 seconds to come back down. It takes about 4 seconds, right? If you're moving upwards at 35 meters per second, what will be the upward velocity after 1 second? Harrison? About 25. After 2 seconds? After 3 seconds? How long will it take to stop moving upwards? About 3.5 seconds. And then it's got to come back down. So 7 seconds we can sort of estimate as the time it's going to be in the air. Does that sort of make sense? Okay? Now, just to kind of ballpark things. If the sucker is in the air for 7 seconds, how far will it go horizontally? Well, how fast is it going horizontally? Trevor? Going, no calculators, we're just ballparking this. It's going about 60 meters every second. And if it did that for 7 seconds, about how far would it go? Somewhere in the 400 what? Yeah, somewhere around 420. Does that sort of make sense? So if we know how fast it's going upwards, we can figure out how long it's going to be in the air. And if we know how long it's in the air, and we know how fast it's moving sideways, we can figure out how far it goes. Okay? So that's going to be our strategy. So the third thing we're going to do here is we are going to solve for the exact time. So delta y equals the velocity in the y direction initial times the time, plus 1/2 the acceleration in the y direction times the time squared. And we want to solve this for t. How are we going to solve that for t? Can you get t by itself? come on, help me here. How are we going to solve that for t? What's your guess? Couldn't? Well, who got it in the warm-up? How'd you solve for t? Jacob, you got it. You use the quadratic. You can solve it using the quadratic, okay? Because this term is not 0, you can't extract the root directly, right? You can't just solve for t. But you can use the quadratic equation. But it turns out, what's c in this case? In the quadratic equation, here's a, here's b, what's c? Change in y, which for our problem is 0. That's a special case. When this is 0, we can actually still solve it. Okay? So we're going to get 0 equals, this term has a t, and that term has a t. We can factor it out. We'll get t times velocity in the y direction initial plus 1/2 the acceleration in the y direction times time squared. So, yes?
Wouldn't it just be times if you factor it out?
Thank you. Just time, I factored the t out. So, when the product of two expressions is 0, then either one of them is 0 or the other one's 0, right? If I tell you a times b is 0, then you know one of those has got to be 0. There's no other way, right? So that means that two solutions are either t equals 0 or this mess equals 0. Velocity in the y direction initial plus 1/2 the acceleration in the y direction times time equals 0. So we can actually solve this for t, right? Bring this to the other side, multiply by 2, divide by the acceleration in the y direction, right? So I can actually solve this. T will be minus the velocity in the y direction initial, oops, I'm going to put a 2 there, over the acceleration in the y direction, which is negative g. That's going to be 2 times the velocity in the y direction initially divided by g, because the negatives cancel. So you don't actually need the quadratic unless a, b, and c are all non-zero. If one of them's 0, you can solve it another way. Okay? You only need the quadratic if they're all not 0. All right, so let's plug this in. What do you get here? Take 2 times the velocity in the y direction initial, divided by g, and who have we not picked on yet? Jack! Come on, Jack, get your calculator. We're waiting on you now. You got it, Izzy? Try it. Take 2 times the velocity in the y direction initial, which you have up here, divided by g. What do you get, Joey? Rayanne, you got it? 7.14? Is it 136? Okay. I'm going to round it to that. And that's going to be seconds. Now, we're going to use this later on, guys, so store it. I recommend storing it in T. That would make sense. But you can store it in Z if you want. We're going to use it. And when you use the number in a calculation, you want to store it. Okay? Because if you use a rounded number, your error grows. So everybody got that stored? So let me just do a quick little exercise here. What's 10 squared? 10 squared is 100, right? 10 squared is 100. What if I took 9.9 and squared it? What do you get? How would you calculate there? What's 9.9 squared? What do you got, Kennedy? 98.01. Okay? So, if this is off by 0.1, when you square them, how much are you off? You're off by 2. your error grew from 0.1 to 2. When you use a rounded number in a calculation, your error propagates and grows. Okay? So when we do a calculation, and we're going to use that later on, don't round it. Okay? When you report an answer, you got to think about significant figures. But when you're using a calculation downstream, don't round it, because any error you introduce by rounding will propagate and grow and grow. Okay? Does that make sense? So we want to save this. So hopefully, if you don't have a TI graphing calculator or a Casio and you're not sure how to save, we need to look that up. So I don't see too many, but there's ways to store the answers. So we got to figure that out. So, got that stored? Okay, so there are two solutions now. One solution is 0, one solution is 7.136. Which one do you want to use? Jake? Which one do you want?
Zero.
Excellent. 0 is a great solution. Here's what we're asking. We are asking, when is the mortar on the ground? That's what we're asking. And there's two answers. One answer is Jacob's answer, and that is before you light the fuse, right? At the beginning of the problem, 0 is a valid solution. It's one of the two times when the mortar's on the ground, at the beginning of the problem. Unfortunately, it's what we call a trivial solution, okay? We don't want to know when we light it. We know when we light it. We want to know when it hits the ground again, and that's the other solution, okay? So you can't just throw out the negative one because there's no negative, but that's the trivial solution. We want that solution there. All right, so this is the algebraic expression. There's the numerical value. Now, we know exactly how long it's in the air. We can evaluate the x problem. Delta x equals the velocity of the x direction initial times the time, plus 1/2 the acceleration of the x times the time squared, because we're trying to find out the range, how far it goes. There is no acceleration in the x direction, and so the distance it travels horizontally is the velocity initial in the x direction times the time. Now, let's put this together algebraically, because I want to show you something. What was the velocity in the x direction initial algebraically? Ellie? Yeah. So this is the initial velocity times the cosine of theta. That's the initial velocity in the x direction, right? What was the time algebraically? It's 2 times the velocity in the y direction, which is v0 sine theta over g. So this is an algebraic solution, right? It tells us how far it goes. We can clean it up a little bit. We can write it as 2 times the initial velocity squared times the sine of theta times the cosine of theta, all divided by g. And that's what you found in lab yesterday. How did the range of the projectile depend on the launch velocity? It was proportional to the velocity squared. Did you get that in lab? So that's the algebraic solution. We call this the range equation. If you want to know how far a projectile is going to go, take 2 times the launch velocity squared times the sine of theta times the cosine of theta divided by g. And just because trig is fun, anybody remember the trig identity for the double angle formula for sines and cosines? No? Oh darn. Turns out that 2 times the sine of theta times the cosine of theta is just the sine of 2 theta. So if you use that little trick, you can say that the range of a projectile is the initial velocity squared times the sine of 2 theta over g. Okay? So that's the range formula. It only works, though, when you start and end at the same height. If you don't start and end at the same height, you can't use this as your time. I'm sorry, you can't use this as your time. Okay? All right, so let's finish the problem, though. Numerically, take the velocity in the x direction initial, 60.6, times the time which you stored, 7.136, and what do you get when you put all that in? 400 and, somebody's mumbling, I can't hear you. Anybody? Got it there, Izzy? Take the velocity of the x, 60.6 times 7.136. You did the whole thing? That's okay. You got it there, Jack? Is that what you got, Izzy? It sounds, so we thought 420, right? So 432 sounds like it's in the ballpark. So I think it's 430, I don't know what, 32 meters or so. And you can get that doing this, or you can get it plugging in those two numbers. Okay? Alright, so that's how we solve a projectile problem. It seems like a lot of work, but it's not too bad. And now you can figure out exactly how far a projectile goes. Okay? So we're just putting together all these things that you know with a little trick, right? All right, that's my first example. The second one's going to go a lot faster. So I got to move the camera here, sorry. Put it behind you guys. Don't do anything embarrassing.